All right. Hi, everybody. I'm Gloria. I'm from the GetCoin team, and I am with Bernhard from Fluence. And we're going to start the Fluence workshop here in a moment. Before we get started, just feel free to drop any questions that you have in the chat. I'll monitor the chat as we go along. And this session is being recorded, and we'll be uploading it on our GetCoin Media YouTube channel. So if you want to come back and refer to that, that's totally fine. With that, I'm going to hand over, let me make sure. Yeah, I'm going to hand over hosting privileges back to you, Bernhard, so that you can get started and share your screen.
All right, let's do it. All right, I'm the host. All right, thanks, Gloria. I'm Bernhard. I'm with Fluence Labs, and going to walk you through a little bit of a workshop today to get you to optimally prepared to solve some challenges and claim some prizes. And what we're talking about basically today is going to be building Web3 protocols with Fluence and Aqua. If you have any questions, as Gloria said, pop it in the chat and we'll get to it. We don't have to wait until the end. And so let's just dive right into it because we got an hour, and for me, even an hour is usually not enough. So I tend to veer off. So basically, what Fluence is a peer-to-peer application platform. It allows you to create applications free of proprietary and centralized intermediates, which gives you sort of the obvious benefits of staying in control of your data and being at least operating in a resistant environment to interference, whether it's control, whether it's from state agents or private companies. And that type of censorship resistance, it's not easily available in most Web2 solutions. And even though Fluence is an off-chain solution, it does provide you those privileges, and that those are, at least philosophically and hopefully or also economically, good reasons to look at those kind of peer-to-peer solutions Fluence provides. And what Fluence provides, in fact, is a peer-to-peer development stack, so you can program peer-to-peer applications, workflows, and compose services. And we'll go through all these things in detail because that's really what it's all about, to build these protocols and applications. And just to set the stage right away, so Fluence, the protocol is a compute protocol, and in that sense requires, or at least encourages, developers to bring their own their storage or persistence layer. And there are some really, really good peer-to-peer storage solutions like IPFS, Filecoin, and a lot of really cool projects that build on IPFS like Ceramics and Textile that are super useful to combine with Fluence, to complement Fluence, and really enable a really wide variety of decentralized use cases. So Fluence in a nutshell. So on the right, we get a little peer-to-peer network, and you can look at the green circles as clients. Could be a browser, could be an IoT device, could be an edge device. It doesn't really matter. And then we get some nodes in that network that they operate peer-to-peer, they interact peer-to-peer, and those nodes can host services. Services are WebAssembly modules fundamentally, with some additional information, and they can be executed using Aqua, which is our distributed peer-to-peer programming language. Now, I know one node here reads relay, and relay is required when is a publicly accessible node in the peer-to-peer network that either allows you access to nodes that are, for example, behind an app that are not directly accessible, or allow you to connect to clients like a browser that are also not directly participating in the network. So that's peer-to-peer network. As I said, it's Fluence, it's open, it's permissionless. You can just join with a node. Nobody gonna exclude you from it. And but there are a lot of valuable assets, services, APIs, and other protocols that are not part of the network. And you can fully utilize those resources through writing adapters, for example. And so you would write a WebAssembly adapter into some API, a microservice, and of course IPFS. And IPFS is a special case because we have provided everything for you to immediately integrate IPFS. And Well, I'll show you a whole bunch of that examples and some code and a demo later. Now, I said we have Aqua. It's a distributed peer-to-peer programming language. Why do you need something specific to program these services in a peer-to-peer network? If you look at the services, they're hosted on peers. So your traditional approach to reaching resources like REST or JSON RPC actually don't really work if you want to take full advantage of the peer-to-peer protocol. So you need a different way of addressing and accessing these services. And the way this is done within in Aqua is that you address and discover and execute services based on their peer that hosts the services and the unique service ID. And we'll go through this in detail. But the primary point was that Aqua helps you to do this at a very, very high level. It's super ergonomic. And if you haven't suffered through peer-to-peer programming, like at the P2P level, for example, then you don't quite appreciate what Aqua brings to the table, but it's super high level. And we truly believe it changes the way people enter and use peer-to-peer programming. So I mentioned Aqua and I mentioned web services. And we have this notion of Aquamarine. Aqua is a construct that includes a programming language, a virtual machine, a compiler, and actually also a CLI. When we talk about Aqua, the programming language, it's a very high-level programming language that actually compiles into an intermediary representation. We call it AIR, Aqua Intermediate Representation, that then executes on the Aqua virtual machine. Each node in the peer-to-peer network runs an Aqua virtual machine. And that is actually how the data model, the data push model we're employing, which is very different from the traditional request response model, we'll get to that in a minute, is actually facilitated. Now, Marine is a general purpose runtime we developed for running WebAssembly IT modules. And WebAssembly IT, as you may or may not know, is very, very different from WAS and BindGen, which you find in front-end development quite a bit. And these WebAssembly modules need their own runtime. And our nodes in the peer-to-peer network run these Marine virtual machines that then execute those WebAssembly modules according to the logical construct you implemented in your Aqua script. Showing it all examples, just going through it. And that enables you to do some interesting things. First of all, you are now separating the composition logic, which actually the workflow that constitutes your application, from your service business logic. So you can, if you had two services, you can change the execution order in your script, fully reuse that service, and actually end up with a different application. And as a result, you of course get in that structure, you get peer-to-peer applications. If you're interested in zero trust frameworks, this comes actually out of the box because the network itself, as I mentioned earlier, is open and permissionless, so anybody can join. So everything has to be zero trust. At any stage, there is no trust whatsoever, and there a record of signatures and verifications is established and takes place that makes sure that a nefarious peer from here, for example, couldn't arbitrarily or not so arbitrarily change the data input into the next service, and so on and so on. So basically, you immediately end up with a zero trust framework, and you end up writing zero trust applications, which is actually really, really cool and a really great corollary benefit of using the system. I talked about the data push model very briefly, and remember the green dots here. One of the foundations of the Fluence system is, or solution is, what we call a particle. Particle you can think of as a smart packet. And particles are conflict-free replication data structures, and they combine data, execution sequence, and a whole bunch of metadata. The important part for us right now is the data and the execution sequence. So if you indulge me and imagine a service, a WebAssembly service, a Hello World service deployed on some node out there in the peer-to-peer network that takes one parameter, name. So let's just say the value associated with the parameter is Gitcoin. So if we call this service with this parameter, with this value as parameter, we end up with hello Gitcoin. That's our service. Very simple, should be very familiar to everybody. So when we start out creating this initial particle, this smart data package, on our client, we start out with a data value of Gitcoin, and then a compiled Aqua script that tells us where to go in order to execute that service. And what happens then is we take this data, we go to this node, or this peer where we need to be, where the service is located, we start executing it on the Aqua VM, and then underneath the WebAssembly modules start doing their thing, and all of a sudden you come out with the hello Gitcoin instead of just data. Data being the value of the input parameter. There's some signatures around this, there's some guarantees around this, and so what you end up with a very secure and verifiable execution chain of state changes throughout your Aqua workflow, which gets compiled into air and executed on the various Aqua VMs associated with the services on those different nodes as specified in your script. So what you end up basically is we end up with the data push model. So what we're doing here is, come on, give me a cursor. We start out with value being Gitcoin, and we push this particle onto that service, onto this peer with the service we anticipated to host that function that now turns Gitcoin into hello Gitcoin. And then this back there could be just your client again, or some other service that consumes that output. And so instead of your traditional request response model, you end up with a data push model, which is actually super effective and efficient and allows you to deploy very, very thin clients if you want to, which is critical for IoT devices, general population access to services, and of course, edge devices. So in order to get all this done, you need some tooling, and Fluence provides that. It's all open source. It's extremely permissively licensed. So it's MIT / I think either MIT or Apache 2. So there's no GPL3, nothing. It's as I said, it's very permissively licensed. And let's just start with the Rust SDK. So we have a Rust SDK that allows you to write those WebAssembly modules. WebAssembly IT is geared towards the backend for its own runtime, not to be executed solely in the browser. And it has a type limitation that actually makes it very easy to write these services in Rust. If you haven't written in Rust and you heard all about these lifetimes and generics and all this difficult stuff in Rust, don't worry about it. In order to write these Rust services, you literally have to only do the first 2 or 3 chapters. If you've done plenty of JavaScript, Go, or Python, you should actually be able to learn what you need to learn about Rust from the examples we have in our GitHub repos. Maybe glance at the documentation a little bit, but I wouldn't expect you to spend more than 4 or 5 hours learning Rust in order to be productive in writing WebAssembly modules. And in addition, the SDK provides some really, really cool extensions of Cargo Test. So Cargo Test is the Rust testing environment, and it usually lets you, what it does, like most tests, unit integration, whatever, you test the code. However, since our compile target is our WebAssembly modules, what we wrote is an extension that actually lets you test the actual WebAssembly modules, not just the code that led to the creation of the WebAssembly module. So what you're testing is actually what you deploy, the WebAssembly modules. And that's actually really, really cool. If you think through it, it's actually really, really neat. And it's a great step towards improving your development experience. It also brings a REPL, so you can interact with those WebAssembly modules locally. which also is very effective because otherwise you would have to deploy every time you want to change something. And so you can interactively check your work. You can do some tests and without ever having to deploy to the network. And the REPL basically wraps that marine environment we briefly touched on locally. So that was the nutshell overview of the Rust SDK. We also have Fluence.js. So Fluence.js is interesting, and it's probably a lot more accessible to many developers right now as opposed to Rust. And it allows you to do two things. It allows you to write a client, a client peer to interact with the network. So for example, to literally spawn off or fling off your Aqua script and then send it out to the network and get all the steps processed and then take the answer back or the result back, the state change back. Or you can actually write a node that's a long-running process. And in the way it is done is that Fluence.js provides you an instance of the Aqua virtual machine. It does not provide an instance of the Marine runtime. So you can't arbitrarily deploy other services, WebAssembly modules onto that node. However, there's some interesting special use cases for these kind of what I call special purpose nodes or special purpose services. And one of them, for example, is the creation of a signing service. So if you interact a lot with blockchain and you want non-interactive signing, using your own node is critical because even though in Fluence everything is end-to-end encrypted, the decryption takes place at the peer-to-peer level, which is actually the node level. So there is this gap of data exposure between the node and the consumption of your hosted service. And that basically would require you to run your node, but you don't necessarily want to run a full-fledged node if you're not interested in hosting somebody else's services or host a whole bunch of services. And when it comes to my keys, I like to have them close to me at all times. I think most of you will agree with that. If you don't, then you haven't been around long enough with keys and wallets. And that's where, for example, writing a Fluence.js node, it comes in really, really handy. So you have this long-running process. It's a node app wrapping around Fluence.js. And you could wrap, for example, Ether.js in it. And then you have your non-interactive signing service. And the cool part is that through Fluence.js, you can expose your local functions, your JavaScript functions, as if they were services, hosted services, and you can fully consume them and interact with them using Aqua. So there's a seamless integration and no differentiation from the workflow development and the service composition perspective between hosted services and Fluence.js services. There's zero. So since from a hackathon perspective, I presume most people are gravitating towards this, I just wanted to let you know. The biggest drawback is that you can't deploy arbitrary services because there's no Marine runtime yet. We hope to change that, but as of right now, as this hackathon, there's nothing. Then we have Aqua, and we'll dive into Aqua a little more. So it's a high-level language that allows you to call these hosted distributed services that are flung throughout the network. It provides a compiler that results in the intermediate representation, the Aqua intermediate representation, and it includes a CLI, so that actually lets you use the Aqua as a client into the network. So it's a really, really great package. Now to Aqua, the language, which is so this was a long build-up of theoretical concepts to finally get into the nitty-gritty of what you probably are coming here for or have come to learn, because you definitely want to tackle those challenges and cash in on those prizes. So let's just go right through the code. If you look through line 1 through 2, so you got an interface. So indulge me and imagine you have a greeting service hosted, written as a WebAssembly module, hosted on some node, and it takes two parameters, a string and a Boolean. The string is basically your name, and the Boolean is the greeting type. So what this super duper service does, it basically says either hi or bye string, depending on the Boolean. So if our string is again Gitcoin and our Boolean is true, then we say hi Gitcoin. If the Boolean is false, we say bye Gitcoin. So super, super complicated. And this is our binding. So basically we declare it as a binding or as an interface. And this is our service ID, which we need, and that's unique. And there's one or more functions. So there could be greeting 1, greeting 2, whatever else you want to associate with this particular WebAssembly module. And then lines 4 through 8 is the actual Aqua script. So basically what we're saying is we have a function, we create a function called greeting. So there's no name clash here. And we give it the following parameters: a name, which corresponds to that string, a greeting variable, which parameter, which corresponds to this Boolean, the peer ID, and the actual greeting service ID. And what we then specify, what we're saying now here is on this node, on this peer that's specified here, we create a binding of this interface with this service ID to the actual WebAssembly modules, to that service associated with the WebAssembly module hosted on this peer. And then we go take this binding, call that function with our specified parameters, get the result back, and then return the result back to wherever our client was. And that's it. So I see something in chat. Okay, I'll come back to that in a little bit, okay? I will not forget you. And so this is where we're at. So this is all you have to do. So if you ever done any network programming or peer-to-peer programming, this is, I don't know, if 2021 is where we're at, then this is 1,000 years ahead of anything else. Or you can say if 2021 is the peer-to-peer, then we're like in I don't know, in the year 2050. I mean, this is how much more high level and accessible Aqua makes peer-to-peer programming. And if you think about it, if you look at it from the diagram here, you basically, you have your client peer, you may or may not have a relay node, and you initiate the service, you call it, and then you get your result back. And that's it. And I don't know, I'm super excited. I think Aqua it's just awesome. And I really hope you all gonna try it, because if you ever want to do peer-to-peer programming, it's never been easier to do it. All right, let me get back to my slides here. Now, we have a bunch of, not a bunch, but we have several available integrations where we already did all the work for you in various stages. So we wrote the services, we wrote certain Aqua scripts, and those are building blocks that are available to you for the hackathon and beyond to just take full advantage of. Everything, again, is open source. It's, I think, Apache 2 or BET or MIT. So there are no restrictions on you to using it. And let me just quickly go through the various, or through a few examples. First, we have a Fluence IPFS integration. It's really, really cool. Alexei did it, and it's really, really cool. And we basically, or he basically built all the services that you need, and they're already pre-built into the reference nodes provided by Fluence. So you don't even have to deploy the services. They're there for you to use. And in addition, we provide IPFS sidecar node as IPFS nodes as a sidecar to each Fluent peer. So again, you don't have to do anything. You just literally just have to take advantage of the system. And since everything is built on services and exposed to services that are consumable and composable by Aqua, you have this totally seamless integration where you now can not only program the Fluence network, program your applications, but you actually can program across different peer-to-peer networks like IPFS all in one using Aqua. And it's ridiculously simple. Obviously very excited about it. It's to me, it's like, I love it, and I'll show you a demo in a little bit. And then we have a Fluence Ceramic integration. It's not quite as out of the box as the IPFS one. So we wrote the services and you have to deploy them yourself. But we do provide ceramic daemons as sidecars to Fluence nodes. So at least on that end, you don't have to deal with anything. And again, you can use Aqua to just seamlessly compose across these different networks. And finally, we got a bunch of additional building blocks. So there's a whole bunch of Fluence examples you can use, curl services all the way to some of the community contributions, some of them from past hackathons, including Gitcoin hackathons. So thanks guys who preceded you or who are back for more. And we got an NFT example. We got multiple decentralized identity examples. And one developer is working on a fairly complex Web3 project with Ethereum and Elasticsearch, which is actually really, really cool. They're all very cool, but this one is still ongoing and working on it, Juera. And if you're looking at doing something with Ethereum or indexing, you definitely want to look at his project. Okay, so Ken was asking, how do you deploy the services? In the long term, there's going to be a marketplace environment, but right now and through the hackathon, there isn't. So Fluence provides a test network, and we have some tools. One of them is called FLDist that just lets you lets you deploy services for free onto whatever nodes you want out of the network. There's no charge; you just deploy away. And so, for the purpose of the hackathon, it's quote unquote a free for all. In the longer term, there's going to be an economic model, and there's going to be contractual capabilities between node or hosting providers and hosting consumers. Did it answer your question, Ken?
Yeah, that's great. Thanks.
Okay, cool. All right, so let me switch. And make this bigger a little bit. So what I'm going to show you here real quick is an example of what you can do with Fluence, Aqua, and IPFS. And as I said, Alexei wrote this, and it's really, really cool. So I pre-compiled most of the things because, as I said, I'm always running out of time. And let's get this show on the road. So what we're having here is we have a web application that wraps a whole bunch of Aqua scripts, and that basically lets you implement or execute almost the life cycle of a WebAssembly service in the Fluence network. So we wrote the service, and now what we want to do is we want to put this on IPFS. We want to put that service on IPFS, just the WASM file. And I'm lazy, so I'm going to use the IPFS desktop for it. So what we just did is I just connected to one of the options that were given in the web form to one of the nodes in one of the Fluence networks. And let me just show you, there's a whole bunch of them. And I just picked one of them. And as a result, I now get back what the RPC address of the associated sidecar IPFS node is, and that's right here. We use that to, no, I don't want to be there. Come on, where are you? To connect the IPFS desktop client to that particular node. So abracadabra, we are connected to this node. And now we want to, we wrote a service, and I'll show you in a minute what we wrote. What we wrote ended up to be this file. And this file is a file, it's the WebAssembly module. And we're going to put this onto this IPFS node that's associated with this particular peer. Now, before we go any further, let me show you the service we wrote. Okay, where is service? Here. All right, so we wrote a service, and the service basically computes the file size in bytes of whatever file you give it. And this is written in Rust. And if you look at it, it's I mean, yeah, it uses some of the standard library functions, but other than that, it's fairly straightforward. And if you look at the annotations here, Marine, those are annotations that basically enforce WebAssembly type conformance, and does a few other neat little things like, not little, but a few neat things like expose whatever's been marked up as a public data structure, interface, or function. So here we calculate the file size, and here we actually write the file size to a file, and then there's some dealing with paths, because basically the way it's structured is you have your file, your data on IPFS, which then gets moved into a particular directory on the node, and then the service, in this case, the file size calculator service, or the files processing service, then access it through the file system on the node. So it's actually really fast, and particularly if your data structures get bigger, it's much more efficient than some of the alternatives. And if you want to look real quick, the way we would build this service is with a build script, which is of course custom. And let me just show this real quick. Basically, what we're doing is we are running Marine build. This is here, this line 9. This is where this is where we actually build the target. And then we just move that target, we copy it to a different directory called artifact, so it's not buried down in the deep recesses of the target release directories. And then we end up with this file, okay? And this file we now put on IPFS. And what we really want to do is we want to deploy this file, this WebAssembly module, as a hosted service on the Fluence network. And this is what we're going back to our form. So, sorry, what we need here is we need the unique content identifier, which you see here, and we copy that in that form. And now we're deploying the service. So super quick. And now this WebAssembly module is available for us to process other files. So let's just see. Let's test it. I know it works, but it's always exciting to test it. And let's just find another file we want to test. And the cool thing, of course, is the file could be anywhere, including IPFS. So if we grab this file and we put this on IPFS, we get another content identifier right here. So we get 431 bytes, right? Keep that in mind. And we now we didn't change the IPFS node. We're still in the same one, but our CID changed, and now we put it in, and oh, look at this. The file size is 431 bytes as expected. So this is actually really nice. And so this is cool, right? So you write your services locally, you put them on IPFS. If you want to use a pinning service, they're obviously available everywhere or longer. And you don't have to worry about your local storage. But the really cool part is actually what's required to get all this done. And for this, we have to look at the Aqua code. So I'm gonna make it a little smaller. If it's too small, let me know and I'll make it bigger again. So in the vein of the Aqua example that I provided earlier, which was just this little greeting service, of course, we have a little bit more to do. But let's just start with deploying the service. What does it take to deploy a service using Aqua? Not much, actually. It's a few lines of code. So again, we need to know where we're at. So we need to know the peer ID. We need to know the content ID, which I showed you before, and we need to know the IPFS multi-address, which we also got. And then we actually, the next parameter is literally a callback for any kind of errors. And then we end up with, optionally, with a service ID. So what we're saying here is on this particular relay, on this node, on this peer, we get the result using IPFS get. So this is a wrapper around IPFS get. And basically it takes, just like the original, it takes the CID and the IPFS multi-address. And that gives us the result for the downloading the WebAssembly module. If that is successful, we now create a service. And what is a service? A service is actually a logical construct. It's a logical construct that's based on one or more WebAssembly modules that are linked, optionally, by some JSON captured instructions. So the way this works, the way you build a service, first you have some module, which is up here. And then for these one or more modules, you actually create what's called a blueprint. And this is basically, these are hashes and hashes of hashes. So you end up with a blueprint. Now, why is the blueprint not the service ID? Well, you may want to use that service more than once on a particular node or throughout the network. So in order to reuse your resources uniquely, you want to associate a unique ID with the blueprint. So for example, if we had this file size, just like we have, and we wanted to deploy this 5 times, even on the same node, on the same peer, so we could process files in parallel, which Aqua allows you to do, you want 5 unique service IDs. And this is what it gives you. And therefore, the service is actually just a logical construct that overlays the underlying blueprint that captures the actual WebAssembly resources and their relationship to each other. And this is exactly what's happening here when we deploy the service. So Alexei really made it really super easy to read. You create the hash for the module. You then create the blueprint for those module hashes, could be more than one, and then you actually create the new service ID, which is actually just a UUID for it, I think. And so now if you wanted to run the service in parallel on the same node, which you actually can, it's a recent advancement, which is also very cool, you basically would instantiate those bindings like you saw in the earlier example over those 5 different service IDs, and then the execution goes over to the very same modules that are allocated to that particular blueprint. That's why the service ID is different from the blueprint. I told you I tend to veer off, but maybe it's helpful if you're getting into deployment. And then you actually want to put the file size. We want to get the file size. So up here, those few lines, it was all that's needed to get the data from IPFS. In this particular case, it was a WebAssembly module, and then actually deploy this module as a service for general consumption, in this case, on a particular node. And you could, as you can say, you could like parallelize this on multiple peer nodes and do the same thing, and deploy this on 5 different peers by basically having more IDs here, and then adding a 3-letter word called PAR, P-A-R, for parallel, and off you go. On the file size calculation, if you look at it, it's also super succinct and a little longer signature, so it looks longer than it actually is. Again, we need the peer ID, we need the actual CID of the file we want to process. We want to calculate the size of. This is not for the service. This is for the file. We want to calculate the process. You get the IPFS multi-address. You get the service ID, and then we can log the size. And if we have any errors, then we do the errors reporting as a callback. So again, on the relay, we are on the peer ID. We get the data just like we did before, just like you would in IPFS on the CLI. If it's successful, we now execute against this binding here. Here we bound that process files service against that service ID, which is coming from here. And now we just execute the file size against that path associated with that data. And then if everything's successful, we just start writing this back into the React app. And co means, oh, come on. I can't believe it. I'm stuck. All right. Writes it back to the React. I can't believe I can think of co. Are you on, Alexei? Put it in chat. I'm stuck on the word. A coroutine. It's a coroutine. Jesus. Sorry. It's a coroutine. Can't believe it. Anyway, stuck. And so you have a coroutine that writes it back to your application while the rest executes. And then we actually also, you saw the write service. So we write the file to size, and we actually can put this back onto the IPFS node we wrote on. And again, if something goes wrong, we have these coroutines that just pop out and write the errors back to the client. And then at the end, you get the result. And to conclude the lifecycle management of this service or module, we actually can remove it. And if I haven't got, okay. So if I haven't, I haven't closed it. So we actually can remove it and it's gone. And that was exactly, again, all you needed was the location, the PID and the service ID. And then you could use the built-in services that are provided through an import file for you by us, and remove that service from the node and move on. And you've been a good citizen by doing that. So that was IPFS. Are there any questions on IPFS?
Do the nodes have to have their own IPFS node?
If you want to use this system, yes. Because the linkage between the data transfer from the node to the Fluence node is critical. Otherwise, however, you could use just HTTP API, and then you wouldn't have to. But this is based on the CLI API, so you want to have it close to the Fluence node. Now, if the addressability, it doesn't have to be sidecar to the Fluence node. As long as you have the multi-address, you're fine.
Okay.
So the other example I wanted to show you, because it just shows you, it's almost like stepwise, where you go from a fully available service Lego provided by us to something a little less inclusive, and that's ceramic. So if in ceramic we build services, and they use both the CLI and the HTTPS API, because they're actually both not fully complete, and you kind of need to use both in order to get your job done. And this is just the code for you to use, and then you would actually have to deploy those services to whatever nodes you want to, and then you can just use it with Aqua. So like here would be a demo. So once you deploy the services, you have there's a few of the functions. So this is the service, this is your interface. These are the various functions associated with the interface. And then if you want to do a round trip, you basically, you just have your payload, whatever your dict is, your KV value, whatever you want to put on. Then we get a payload too, so we can test update, and then, the node and where the service with that particular service ID is hosted. And again, it's just super simple. I mean, you're out there, not out there, but your code is out there, your script is out there, traversing this peer-to-peer network, going to these different services, or in this case, it's just one, but going through these different services, and you control this with like 5 lines. And again, you establish the binding to the interface, and then you just start calling your functions associated with the service, and off you go. And then at the end, so here we get a triple return that gives you the various the create result, the update result, comes last, and then in between the show result for the actual commit to the stream in Ceramic. So, and again, like if you compile it, in this particular case, you end up with actual 2 WebAssembly modules. One is the Ceramic adapter, which is based on the code, the Rust code that I showed you. And then we have an additional WebAssembly module, which is a curl adapter. So now I got to go backtrack a little bit. Why do we need a curl adapter? WebAssembly IT modules are, like all WebAssembly modules, don't have sockets, and they're single threaded. So they're extremely limited. And on top of it, WebAssembly IT modules are heavily sandboxed. So there's a high level of security. That's great, but that really doesn't help you all that much to interact with the outside world, right? And we want to interact with the outside world. So what we've done is we've created a permissioning system that, if properly implemented, allows a service to access resources on the node. Such a service could be a curl call, a curl binary, or it could be a Fluent, an IPFS CLI, or a Ceramic CLI for that matter. Whatever you want, as long as it's permissioned properly, within reason, the service has access to it. So basically, you can make calls out from your service, and this is where the curl adapter comes in. And what we need to do, just to show you this really, really quick, because if you may run into this in your hackathon requirements, we on the CLI side, we need to link into the host system's Ceramic CLI. And for that, we don't need an adapter per se, but in order to access the curl adapter, we use a WebAssembly module for the curl adapter, and we link that in like so. Very super simple, super simple. Hey, sorry, UPS coming, hey. And that's it. So are there any questions on IPFS or Ceramic? I'm freaking out because I only got 9 minutes left.
You can take as long as you need, Bernhard.
Well, I'm sure people have, I would, but I'm sure people have other plans than hanging around for hours here. So
I do have just kind of a broad question.
yes.
Can services access external resources? Like, for example, can a service interact with the Ethereum blockchain?
Yes.
Okay. So
let me show you something. Let me show you something real quick. No, that's not it. Too many windows, too many windows. Okay. That's not an Ethereum example, but that's a near example I've just been working on. And there's no difference to Ethereum. So basically what you want to do is you want to wrap the RPC calls and execute them with curl. That's really what you want to do. So let me just
okay, so I wouldn't want to use the Rust library, what's it called? Rust Web 3 or something.
Okay, so you can try it. So the problem with a lot of the Rust part is that if there's a lot of C underneath it, you have a problem compiling it as a web service, as a WebAssembly module. And the other part is, so the Web3 module, all the Web3 modules in Rust, like, and even same in Python and in JavaScript, they're all extremely closely tied to the transport level. So the transport is really your entry into the Web3 modules or libraries or SDKs. And peeling that apart is actually extremely complex.
Okay.
And so you're actually better off using JSON RPC calls, or particularly if signing is involved, use the Fluence JS toolkit. Because then you can actually wrap ethers.js, for example, right into your Fluence JS code. Okay. And you then expose the interfaces you want to expose, which don't have to be all Ether.js, if any, API calls to the network that can be consumed with Aqua. And let me show you something else. This is also near, blah, 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 blah. This wasn't, okay, this is the wrong one. Okay, here's the signing out, hang on, VS Code. Okay, so this again, as I said, I was just working on it right before the call. So here we're using, let me close this so I get better look at it, so you get a better look at it. Here we're using Fluence.js to create a signing node with near. So we're using the near API, we imported it here, and you could do the same thing with Ether.js. And I actually have an example, hang on, I have an example of doing that with Ether.js.
That's okay. I'm just trying to get a sense of what it's capable of. I'm working on a project right now that has the need for it's an Ethereum project, but it needs to have a private server, private-ish server.
Yeah, so this is where you want to go. So there is let me hang on, let me put this for you in the chat. I don't see the chat because I don't, okay, here it is.
Thank you. I also was thinking about part of what the application I'm building is, the reason it needs a server is it needs to store secrets.
Yeah, so you definitely want to use the Fluence.js for that. You definitely want to. You don't want to have your secrets out there.
Right. Well, so I was thinking about maybe even bridging over to the secret network, or
well, a secret network would be a network that you control, probably behind a NAT, where you run all the nodes. And
no, I'm talking about the secret network.
Okay, sorry, okay.
Or NewCipher or something like that.
Yeah, NewCipher is interesting in that sense because of the re-encryption, but yeah. You get the delay of when you back it with the blockchain, you get the delay of getting finality on your on your keys.
Of course.
So if the verifiability of your, let's just call it re-encryption, is critical, then NewCipher would be an extremely useful way to go.
Mm-hmm.
If all you need is a transaction that's signed and processed on chain as a proof for whatever you needed to be done got done, then you probably are just as well served by just running your own Fluence.js node than going outside.
I see. Okay.
So it depends. It depends on the value and requirement of the proof and proof validation requirements associated with whatever transaction you're trying to process.
Okay.
And you can hit us up in Discord as you go along. I mean, we're happy to. This sounds like an interesting use case. So
yeah, it's digital inheritance is the use case.
Cool. Yeah, so definitely. Also, I'll show it later on. You can book time with the team. We have a calendar for the hackathon, so it's no problem.
Okay.
Let me like go through the prizes real quick, and then we can open it up back to questions. So we get 3 challenges. A beginner's bounty which we have 5 off. They're about $700. They're not about, they're $700 each. And basically use that Fluence JS node Ken and I just talked about as a starting point to wrap a Web3 library or SDK and expose its API to the network with Aqua. So basically, so Ken, if this is the way you're going, definitely start with that, because it gets you halfway to where you need to go on your other challenge. Then we have an intermediate / advanced bounty, depends on how you look at it. And we got a couple tracks in there. One is basically implement distributed services to create interactive signing. So if you're in the Web3 space, you know there's interactive and non-interactive signing, and MetaMask usually is used for interactive signing. And one of the ways to represent human readable transactions, so you actually know what you're signing in MetaMask instead of just getting a hash, comes through the EIP 712 document. And so implementing that, and there's an example I just showed you, actually the one I showed you in the and shared in a chat that already gets you halfway there. Or implement distributed services to create, manage, or verify decentralized identities. I listed a few previous work examples from hackathons where self-ID was used. So if you're interested in decentralized IDs or actually verified credentials, it could be verified credentials as well, particularly on the verification side, we'd be happy to look at you. So if there's anything you want us to ask about, if your project fits, please reach out. And finally, best use of Fluence and Aqua in your dApp. So if you have something you're already working on, you want to work on, and Fluence and Aqua can help you to take out or eliminate some of centralization components, or provide a verifiable off-chain solution that could massively or drastically reduce your cost of transaction, please, this is the category for you. Sounds like Ken, for example, you're in this category. And just do what you need to do. If you have any questions, if you need to reach out, please do. Our website is fluence.network. We have fluence.dev. It's pretty good documentation. We got lots of examples. We're in GitHub. We got YouTube examples. So the IPFS tour I gave you very, very quickly, there's an entire, or at least an entire video on it, and from multiple people. So I think Alexei did one and Mitri did one, so you don't have to just listen to me, you get other voices as well. And we're in Discord, Twitter, just the whole thing. We got a bi-weekly community call if you're interested. We also answer questions during that. And you can sign up for Calendly with us. And finally, we're hiring. We got a whole bunch of open positions. If you're interested in the Web3 space and peer-to-peer networks, please hit us up. And that was it from my end, 4:01. I kind of made it. Are there any more questions before we're done here?
Yeah, I don't see any questions, Bernhard. Yeah, I would just say, yeah, thank you for taking the time to go through this workshop with us as well. And I think that the best thing I could say is that if you do have any questions, please reach out to Bernhard or the rest of the Fluence team. I know he shared the Discord, and they've always been great people to work with for me, and very quick and responsive as well. So join the Discord, take a look at the Fluence bounties. There are quite a bit of prize money to be had, and a great way to be started. So thank you, Bernhard, for your time. And with that, I'll give everyone else back time.
All right, thanks everybody. Have a great day. Thank you, Gloria. It was awesome. And good luck, everybody. Good luck.
Yeah.